Hello everyone, welcome back to Nated Engineering. Today we are looking at gradually applied load. Remember from our previous video when we were dealing with strain energy, we said that there are three ways in which a load can be loaded to an object. We said we have a gradually applied load, we have a shock load, and we have a suddenly applied load. So today we are going to cover the gradually applied load. And to understand what gradually applied load means, we are going to look again at the example of a spring. By having a spring and we are applying the load to the spring, we are trying to compress the spring. As we are starting, the load that we are currently applying will be 0 kilonewton, and then we will work our way up to the maximum force that we are going to apply to the spring. Let's say our maximum force is 100 kilonewtons, and this is an example of a gradually applied load. As the name suggests, we are gradually increasing the load that we are applying to the spring. So it will start from 0, it will go to, let's say, 10, 20, 30, 40, up until we get to the maximum force that we are going to apply to the spring, in this case, which will be 100 kilonewtons. So when we are dealing with our gradually applied load, to calculate for the strain energy, we are going to use the formula that we know, which is equals to 1 divided by 2 F. This will be our average force because we are gradually increasing the load, times the change in length, which will be the total change in length. Now you can express this formula depending on the type of information that you are given in the question. You will need the formula for strain. Hopefully you still remember this. Strain is equals to the stress divided, Young's modulus rather, it's equals to strain divided by the strain, which will be equals to the force length divided by area x, which will be equals to stress length divided by the change in length. Hopefully you still remember this. So here, depending on what information you are given, you can manipulate the formula to make it suitable for the information that you are having. So let's say we are not given, we don't have the change in length, we are given the force. We want now to express the formula in terms of the force. What we are going to do is we're going to say this will be our force, and we're going to substitute here, and we're going to end up with FL, and then it will be A E. You take this and make X the subject of the formula. Substitute here, and then this is in terms of the force. So this and this, it's the same thing. You can say our formula will now be half, let's say just say force squared L divided by A E. We are expressing now our formula in terms of what? In terms of force. Let's say you are not given force, but you are given the stress. You can also manipulate the formula to express it in terms of what you are exactly given. So in this case, you will be given what? Stress. We want to express the formula in terms of stress. We are going to say half. What is stress? It's equals to force divided by area. We have this, we want to express it in terms of the stress, meaning we are going to make the F subject of the formula, which will give us stress times area, which we are going to put here. It will be stress times area. And then we come here. We want to express it in terms of what? Of stress. Therefore, we are going to take this. It will be this, and make the subject and make the change in length subject of the formula. which will give us something like this, times the stress length divided by the Young's modulus. This and this are the same, therefore we are going to say stress squared AL divided by 2 times the Young's modulus. You don't have to cram this. I'm just trying to show you that you can manipulate the formula in such a way that will be suitable for the information that you are given. As long as we are working from this formula and this formula, you can solve any question that you are given in gradually applied loads. This will be when you are calculating for a strain energy of a single object, an object with one cross-sectional area. So let's say you are working with an object that has 2 cross-sectional areas. Let's say you have something like this. You have object number 1. It's the same object, but it has 2 cross-sectional areas. We know that if it is like this, we're going to treat them as separate objects, where we are going to apply this formula. The total strain is equal to strain number 1 plus strain number 2. And we know that the formula for strain is given by 1, it's half times F, which is the force, times the change in length. In this case, it will be changing length number 1. It will be plus half F times change in length number 2. The force, it's the same. Therefore, we are going to take a common factor of half F, and it will be x1 plus x2. This which will be the total change in length. So when you are dealing with an object that has more than one cross-sectional area, you need to consider each change in length separately. So from here, you can apply the formula, which is E Young's modulus, it's equals to stress divided by strain, it's equals to FL AX, it's equals to stress L divided by X. You apply it here, you apply it here. But at the end of the day, here, this is the total. Your formula will, this is the total change in length. Your formula will be like this, half F X total. We then have something that we call the proof, we call proof of resiliency. Is proof resiliency, and it is given by divided by 2E times area times length. And then we have something else that we call the modulus of resiliency. The modulus of resiliency is given by the maximum stress divided by 2E per cubic meter, which will be this part per cubic meter. And then the SI unit will be kilopascal per cubic meter, of course. And that is all that we need to know about the gradually applied loads. I will see you on the next lesson.